Astronomers have been thinking about the moon as a platform for doing astronomy for decades. There have been proposals back into the 60s where people thought about, like, what could we use the moon for our astronomy? And a lot of the early ideas were about setting up telescopes on the moon as part of the Apollo program. But of course, the Apollo program ended with Apollo 17, and we haven't seen any further human exploration of the moon. But people have still considered what it could be really used for. And over the last couple of years, these ideas have started to really come together and gel that the moon is ideal for certain kinds of astronomy. They're actually really difficult from the surface of the Earth. That on the far side of the moon, you are protected by the mass of the moon from all of this Earth-based radio pollution, so you could get a very pristine view to some of the most fascinating parts of the universe, maybe even detect exoplanets through their magnetospheres. The moon is geologically stable, and so you could set up gravitational wave observatories with unparalleled capabilities. So more and more people are starting to realize that, okay, the moon is a really interesting place to put some kind of observatory for us to answer questions that we just can't do anywhere else. My guest today is Dr. Martin Elvis. He is with the Harvard and Smithsonian Center for Astrophysics, and he has been working on advising various astronomical unions, committees about the potential for a series of observatories on the moon. And so we talk about the potential at a very high level. What are the different kinds of observatories that could be put on the moon? What potential science could be done in various realms? And I promise that there's going to be some ideas here that you've never heard before that will sort of expand your concept of what we could do for the moon. And I think could justify both robotic and even human exploration of the moon, just for us to be able to set up and manage and maintain these telescopes to give us these valuable answers. So enjoy this conversation with Dr. Martin Elvis. Martin, when did astronomers start to think that maybe the moon was a good place to put a telescope?
Well, I think there was interest in it back in the Apollo days, but after that, silence, because no one was going to the moon. There was no chance of getting anything. And we also didn't know enough about the moon to realize it had some very special places on it. So, what did he call it? Magnificent desolation was what Buzz Aldrin called the moon when he stepped onto it. And meaning it was kind of a grey wasteland. It was all just the same. But that's completely been turned over by about 10 or 15 years worth of new orbiting missions that have mapped out the surface of the moon in various ways, its temperature, its composition geologically, and so on. And now we realize there are quite some special places that really are very advantageous for telescopes if you get the capability of landing there with some serious mass, multiple tons.
I mean, when you at first blush, when you look at the moon, it is kind of like a space telescope, except it has a horizon, and so you don't get a full 360-degree perspective. And yet we're so familiar with the work that's been done by Hubble, which of course is in low Earth orbit, so the Earth's in the way. But then we're out at L2 with James Webb and Gaia and all of these other telescopes, and they have a 360-degree field of view. And you don't have to try and go down into another gravity well and be able to build on the surface. And like all of the problems of construction suddenly come online with the moon. And yet you've got all these downsides. And so I think, initially it sounds exciting. And then you're like, wait a minute, how is this better than a space telescope? How is this better than a space telescope?
Right. Okay. And I'd always thought the same thing. But there's a guy in France, Jean-Pierre Maillard, who has made a nice list for us of the advantages. If you're assume we're building a successor to James Webb Space Telescope that's several times as big, it'll weigh a pretty enormous amount. And so moving that telescope from one location to one target on the sky to another target on the sky, that takes some huge reaction wheels. You have spinning wheels that do this, so you have to move the telescope in the opposite direction. On the moon, you've got a huge rock you're standing on, and you just push against that rock. So you don't have to have huge and probably dubiously reliable after reaction wheels to work with it. The moon is not going to stop working as a body to push against, and that reaction wheel is really, really good. Then you don't have to have onboard solar panels, which can flex and move your pointing around as it used to on Hubble, but also just you can have much more power on the moon because you run a cable from where you are up to some place that's so-called peaks of eternal light, which are very almost permanently illuminated by the sun. They're always at the South Pole because at the South Pole of the moon and at the North Pole of the moon, the sun goes around the horizon because the moon is not tilted. The Earth is tilted by 23.5 degrees. That gives us summers and winters. But the moon is tilted by like 1.5 degrees. So there is essentially almost no summer or winter there. There's a little bit of change in temperature, but the sun is always going around the horizon. So if you're on a peak at the South Pole, then there's never anything occulting your view of the sun, getting in the way. Now it's never quite true, but it's pretty good.
Yeah, I remember there was a survey that was done where people were searching for peaks of eternal sunlight, and they found the best they could do was there was a couple of peaks that gave you 99, like you would lose like 10 hours of a lunar day.
Yeah, every so often you lose 10 hours or 20 hours or something like that. And if you put your solar panels on a stick vertically, and they only then you get up above a lot. You can quickly get up above a lot of that blockaging. So we did a whole study on that. What else? James Webb was designed for a 5-year lifetime, and that had propellant on board for changing its orbit, keeping it in its desired orbit. And luckily, that's going to be 20 years because they were cautious and they went into exactly the right orbit for the Ariane 5. So, but at some point it will run out. On the moon, you don't run out of. You stay in where you put it. It doesn't wander off. You don't need a complicated sunshade. On James Webb, they had this tennis court sized 4 or 5 layer, I forget which, mylar sheets to block the sunlight to keep it cold. Instead, also at the poles of the moon, you can put your whole telescope in a crater that never sees sunlight. You could call it by analogy a pit of eternal darkness, but they actually called it PSR, permanently shadowed regions, which is a little less poetic.
Yeah, I like pits of eternal darkness better.
Yeah. It's actually more accurate because they really never do see the sun. Peaks of eternal light, every so often it goes quite dark for a bit. But in the pits of eternal darkness, that's 100%, hasn't seen direct sunlight in 4 billion years. And so you keep the telescope cold. You don't have any problem of radiation from the sun on one side. It's thermally stable, although very cold. But cold is good because you want your telescope to work in the infrared, and the colder it is, the more the background is pushed to longer wavelengths by the blackbody radiation. And you servicing something out at L2 where James Webb is really not possible at the moment. I mean, NASA's going to build its next generation flagships so that they can be serviced. It's required to do that. But if it's going to be serviced out at L2, you're going to use robots to do it because people won't last long in that high radiation environment, right? Instead, if you've got a base at the South Pole of the moon already, then you've got people there and they can go on shortish expeditions out to the telescope site and install new equipment, repair things that are broken and so on. So maybe overall, just the total cost through the mission and lifetime, it could even be cheaper to put things on the moon with all these considerations.
I mean, like if one of the astronauts is an amateur astronomer already and they're allowed in their personal allowance to bring a small telescope with them when they go to spend their 6 months on the surface of the moon, and they set their telescope up outside and hook it up, then suddenly they've made a world-class observatory just with their hobby because of the environment, because it is so clear. You have none of that atmospheric nonsense to have to deal with.
You'll be limited, diffraction limited. So you won't have that seeing, the wobbling of the atmosphere that limits ground-based telescopes, and which huge amounts of ingenuity have gone into fixing, but the easy way to do it is get above the atmosphere.
Now, all of these things that you're describing is very much about supporting our kind of traditional concept of an
Mm-hmm.
observatory. You take the extremely large telescope, you put it on the moon. And I
Yeah.
recall, like with the European Space Agency, they were entertaining, they had their visions, Cosmic Visions 2050, which is sort of like their version of the NIAC grants. And they were sort of thinking about what the future holds. And someone had proposed, let's just put the overwhelmingly large telescope
Mm-hmm.
on the moon,
Yeah.
right? And so you've got all of the advantages of a 100-meter class telescope, but you also have all those advantages that you just mentioned, that they're all, so on and so forth. So it's all on the moon, which is one really interesting pathway to go. Then you're dealing with costs and benefits, and like, does it make more sense to put this thing
Yeah.
just in space or so on? Could we build a space-based thing like the International Space Station and on orbit constructed and so on and so forth? But I think, in reading your paper, there are unique use cases that can only be done on the moon. So I'm
Yeah.
really interested. Where do we start to get some reasons why the moon is the only place we could do some of this science?
Sure. The most argued case already that in existence is for the telescope, a radio telescope on the far side of the moon, where the 2,000 kilometers of rock gets between your telescope, and the transmissions from Earth. And so human-made noise, also even from the atmosphere, but ionosphere, but largely human noise regenerating all the time. But the rock of the moon is a wonderful way of absorbing that, and a little bit leaks around the edges, but so it's not just directly on the as soon as you get across the boundary and you can't see the Earth anymore, you have to get a little further than that because of diffraction. But these wavelengths are particularly interesting because there's only one signature we have that we know of from the time before there were stars or galaxies, and that's when the universe was just neutral hydrogen. This is after recombination, when the universe was opaque. The universe is not opaque because it's neutral hydrogen, but what signal are you going to find? There's no stars, no nuclear burning, probably no black holes with matter falling onto them. It just hasn't happened yet. The answer is hydrogen has this one famous line which occurs at 21 centimeter wavelength. Normally, well, it's emitted at 21 centimeter wavelength. That line will tell us we could map out the distribution of hydrogen as a function of time from the
The reionization?
Yes, thank you. Recombination.
And the recombination? Yeah, okay.
Yeah. It's a funny name because it isn't recombining, it's combining for the first time, right? The electrons are finally allowed to touch protons, get around.
Well, I guess they were split up
they
before
never had been
the
together
cosmic microwave background.
Yeah,
Yeah.
So anyway, excuse me. And you can watch that structure develop. Expect gravitation to gradually increase the amount of structure, and you could make a tomographic three-dimensional map of space and time, and watch that happen. And what you would do is see this line in absorption against the glow of the microwave background in the background, which is always in the background. Nothing more background than that.
And this signal, like this 21 centimeter line, which is going to be redshifted out to who knows where it'll be
where I was going to go.
in the radio spectrum.
Yeah.
This is a wavelength that is deeply polluted by humanity?
Not at its rest wavelength, not at its emission wavelength. It's the redshifted thing. As
That's
the
what I mean, yeah.
Expanding, you redshifted by 50, 80 times, something like that. And that gets it right into what we call the VHF band in radio, right? But it's very low frequency to a radio astronomer, and not very high frequency. But it's exactly where the radio stations and TV stations emit.
Right.
So,
right.
And you need to cover it at a whole range of redshifts. So it's not just say, let's save this one radio frequency for this cosmology experiment. You need a wide range to do the whole map.
It's interesting, when people say we want to put a telescope on the dark side of the moon, and you're like, wait a minute, it's not that there's no dark side of the moon. But
Right.
from the perspective of radio missions from humanity, it is the dark
It
side of
is
the moon.
dark, actually. That is true.
Yeah,
Nice. I like it.
yeah,
Yes.
yeah. Okay, so I mean and this is really important. Like I think as fundamental to understanding the cosmic microwave background radiation, which seems to like never stop
Mhm.
giving us a bountiful harvest of science. This 21 centimeter line of this recombination era, the so-called dark ages of the universe, this is when the whole process of universe's evolution got started. So
Mhm.
again, and something that we just can't see right now.
Yeah, absolutely. This is we can get out to redshifts of 10 now with James Webb Space Telescope. We're seeing galaxies at that point, perhaps surprisingly big ones. We don't really know yet. But the only way to get beyond that, to before the time of stars and galaxies, like you said, the dark ages, this is the only signal we know of.
And it's interesting, like, you're synthesizing the opinion of astronomers
Mhm.
and sort of, working with the IAU to figure out some larger worldwide recommendations for what kinds of telescopes the scientific community wants to see going into the future. And James Webb, when it was launched, was really designed to answer a lot of these questions about the early universe. And I think people have been surprised at how this is starting to rewrite textbooks about the early universe, what that first billion years looked like. And so do you see like the emphasis starting to shift over and go, no, we really do need to know what happened in the dark ages. Like this is like whatever created the results that we're seeing in James Webb, we need to understand the forces, the factors that set that in motion.
Oh, I think you got it right. Yes, absolutely. The more we get out, the more we get out to high redshifts with James Webb, the more the mysteries add up, and it's like, wait a minute, how did that happen? And you
Right.
need to go back in time further, and of course, that eventually takes you before there were any stars or
Yeah.
galaxies.
How do we get a black hole with a billion times the mass of the sun at 700 million years after the Big Bang? How do,
Yeah.
how,
The origin
like,
of giant black holes. That's one of the things I actually work on, and it's baffling. It's
yeah.
really strange. We know where small black holes come from. That's easy. Ha! It only took us 30 years, but where the big ones come from, it's still a mystery. And ever since what 1967, 69, when we first people said, "Oh, could be a giant black hole powering a quasar,"
Yeah.
still we don't know. So that's 50 years or more.
If you rewatch Cosmos,
Hmm.
1982, I forget when Carl Sagan did it, and he is talking about quasars, and he's like, we don't know what they are. They might be black holes, but they might be alien civilizations sending their spacecraft on voyages, and he comes up with a bunch of ideas, and I just yell at my computer screen like, they're black holes. We know what they are now. um,
Yes.
but okay, so I think that is really powerful. So what kind of telescope, what kind of observatory gets us insights into that redshifted 21 centimeter line from the surface of the moon? What does it look like?
Right. So to begin with, you just want to detect it and you get a global signal and so on. Eventually, you'll want to map it out at higher and higher resolution. So you could begin with just a few dipole antennas, just basically wires on the surface of the moon. There's all sorts of technical things to worry about that I'm just learning myself, actually. Like what kind of rock you're putting your antenna on matters because it's not completely inert.
Oh,
It
right.
can
And it's like
reflect.
it's all various kinds of metal mixed in with
Yeah,
oxygen.
right. So it's not trivial. You may want to mount it above the surface or have a layer underneath that is metallic to suppress the signals, and then the real design gets complicated. But in the end, to get the total maximum information out of this system, Joe Silk in particular has been arguing that you need to get down to the size of about 1,000,000 times the mass of the sun, 1,000,000 solar masses, from which these gas clouds of hydrogen, from which will then merge into galaxies, and that will give you, because there's a 10 to the 12 or so solar masses of a galaxy. That's about 1,000,000 times more information than you can ever get from just measuring galaxies.
Hmm. So
The
just
map
to
will
sort
be
of clarify that,
fabulously detailed. Yeah,
you're talking
sorry.
about the resolution of this telescope
Yeah,
needs to be able to resolve features that are about 1 million solar masses, like I don't know, like a large globular cluster or
globular
something.
clusters kind of
Right.
mass. Yeah,
Yeah. Okay.
absolutely.
And then that tells you that those are the seeds that you can
Right.
then understand
Yes.
how the rest of the universe evolved.
Right. So, but to do that, you need to get a few arc second resolution, maybe 10 arc seconds would be good enough. And of course, at low frequencies, that means a really big telescope. And the estimate is it's about 200 kilometers in diameter.
Right.
And you think, well, that's easy enough. Look at the moon. There's plenty of places to put it, but
I
not
don't
on
feel
the
like
far
that's easy
side.
enough.
The
Yeah, I
far
don't think
side,
that's
as you know, is totally different from the near side and very mountainous. So there's only a few places that are big enough to that you could land a rover and then unfurl loads of antennas going over that kind of distance. Uh, we did a study and found, well, there were maybe 8 candidates, and then we look at the lidar data from Lunar Reconnaissance Orbiter, the LOLA instrument, and we found that the ability to drive along them, it has to be, it requires that a rover never has to go up more than like a 15-degree incline, because that's all they can do, so at least so far. Maybe 20, but most of the even flattish areas on the far side of the moon just aren't that flat. I mean, it really isn't that good. And then there's also a lot of noise in the data, which is not really noise, it's boulders. And so there's a lot of surface roughness that we had to deal with. And we need to do much better mapping, but we ended up with maybe 3 places you could probably put this.
right. It needs to be on the far side of the moon. It needs to be in an area that is not incredibly mountainous and not too boulder strewn, and a place that maybe we can access
Yeah.
to be able to land a probe, because different parts of the moon require different
Yeah.
amounts of propellant, delta
And
V, to
also,
actually
you,
reach.
you, you want to look at if you look at the sky in these wavelengths, there's an enormous amount of emission from the galactic plane, and that's loops and filaments and things all over. And there's a few areas which look particularly dark. So you want to put your telescope more or less at that declination. And so that will, and because there's no tilt to the moon, that translates into latitude on the moon. So that's another constraint that has yet to be really worked out in detail, but it's a worry.
And so, would it only be looking in one direction, essentially
There are a
overhead,
few,
directly overhead, and then as the moon is orbiting the Earth and the Earth is orbiting the sun, you're getting different parts of the sky passing through its field of view?
yeah, I think there's going to be some limitations. You will never look at the galactic plane, and you want to avoid these loops and things. And so there are going to be some fairly substantial areas, like tens of square degrees, a few places where that's pretty dark. The galaxy is dark, and so those are your prime locations. And then optimizing an observing program to fit that is you certainly want to be at the right latitude and declination. But then you're going to have to worry about how it will change. You will scan around over regions that you'll learn a lot about the galaxy, but you probably won't learn a lot of cosmology in a lot of the time there. Though I don't think that's been gone into in any great detail yet. People are still trying to establish that yes, it really is very quiet on the dark side of the moon, right? That would be a great thing to know for sure.
Now you mentioned 200 kilometers
Yeah,
diameter.
yeah,
In right, and I mean that sounds like an enormous radio dish, but we're just talking about laying wires down on the surface of the
yeah.
moon,
Pretty much,
not
it's laying antennae down. There's just a few yards, a few meters long.
and it like is there some ideal shape, or are you making a circle? Are you trying to
Oh,
make like a spiral that you're filling in? I mean, I
I'm
guess
sure there are clever ways to do it, and I'm no expert on that kind
right,
of thing.
yeah,
So
yeah,
yes, basically fill in as much of the area as you can to make as accurate an image as you can. But
right.
I mean, you always will end up trying to optimize it by saying, well, if we put every other one, or if we thin them out as we get larger, or whatever, and to save mass, to save cost.
Right, you're
And
getting this
maybe
baseline
yeah,
versus potentially the kind of brightness that you're able to detect.
right. Well, going to need a lot of antennas just for sensitivity. Yes.
Yeah.
Um, I mean, there may be ways out of this, but once you raise the issue, people get clever about this, and maybe you can land a whole bunch in different places that are individually small but are spread out by the right amount. And you don't have a rover to worry about, you just have a local thing that unrolls. And then they would have to communicate with each other, but maybe they do that via satellites going in lunar orbit.
So some kind of event horizon telescope on the moon.
Yeah, I guess that's nice, yes.
Yeah,
Yeah.
yeah. Okay, so I mean, this is powerful and would answer a lot of really important questions in cosmology. Thanks to it being radio quiet. Are there any other really interesting radio observations that we could use to investigate
Yeah,
from the moon?
you could use a big radio telescope working at similar wavelengths to look at magnetospheres of exoplanets, which may be important. A lot of planets have magnetic fields around them, and you see there the particle emission from them, the radio emission from particles spiraling in those fields. That could be important for habitability. The Earth, we know, has a nice magnetic field that keeps a lot of cosmic rays away from us. So that might be a good another filter on, of all the rocky planets in the habitable zone. How many have this? How many have that? And maybe this is one of those criteria for filtering down to good candidates for life.
I love this as a way of exoplanet detection. I mean, we have the transit method, the radio velocity method. We have we have gravitational microlensing and so on. But with radio waves detecting the aurora emissions from exoplanets protected by magnetospheres, it's a twofer. I mean, you are not only detecting the presence of a planet, but you're also detecting the presence of a planet that's protected by a magnetosphere, which is like
Yeah,
one of those things for life, which is amazing.
yeah. And of course, at the same time, with the same telescope, probably you can just do a SETI search because you are now able to detect their transmissions if they're still using radios and TVs and so on. So that would be another kind of perhaps less official. I guess we were coming to a point where we're allowed to talk about SETI completely straight and not have
Yeah,
to
yeah, it's
apologize
fine.
for it.
It's completely legitimate conversation to have now. We can talk about searching for technosignatures.
Yep,
NASA will fund it. Everything is fine now,
yep.
so it's all right.
Big,
Um,
great.
yeah, yeah. You can put the science fiction book down and pick up the science book again.
Oh
Um,
yeah,
uh,
great.
so we talked about like let's put the extremely large telescope but on the moon, or let's build an infrared version of the extremely large telescope. Let's build a radio telescope on the far side of the moon. Are there any other types of observations that we could make from the far side or any part of the moon that would be sort of really useful in astronomy?
Yes, gravitational wave detectors. The moon is seismically extremely quiet, right, compared with the Earth. So, in principle, if you put a gravitational wave detector on the surface of the moon, it can go about 2 orders of magnitude lower in frequency than the LIGO and Virgo Cagra combination on Earth. They're completely limited by trucks driving by and other kind of noise that not all human generated, because we're living on an active kind of tectonically active planet. But the moon, that doesn't happen. So you could build something comparable, perhaps bigger than LIGO on the moon, and it would be sensitive in regions where LIGO cannot go to, and also where LISA, where the ESA mission would not go to, because it concentrates on much longer baselines and even lower frequencies. And it's kind of interesting in this 2 decade range, what you would be able to see are fairly continuous sources of two black holes orbiting each other. And as they, not in the final chirp as they merge, but just as they're emitting gravitational waves and spiraling in. And you'd be able to predict when and where to look in the sky for the actual flash of other radiation, if there is any, coming from them. So you could point your new James Webb Space Telescope replacement out at that location and know when to look and where. So that could be very useful. And I'm sure you'd learn a lot just from the gravitational waves as well.
Yeah, yeah, that's
So,
really interesting. That I mean, right now we're limited. We're seeing these explosions after they happen. We're seeing the supernova after they happen. We're seeing the black hole collisions between stellar mass black holes after they've happened. We had the kilonova, which still after it happened, but at least we got an electromagnetic glow from that as well. So
Right.
you could cross
Just
check
one.
it. Just one. Well, I think there's three now. I think at this point
Oh,
there's
oh,
one
is it?
more.
Okay.
Yeah,
Well, then
yeah.
I can.
Uh, Candidate kilonova, but to see them in advance, I mean, it's funny. Like right now, there's this huge buzz about this upcoming visible nova that's going to be showing up in the next couple of months this summer, and everyone's really excited about this because we can predict that this star is going to brighten, and we know where to point our telescopes, we know where to look, and this is the whole. Like this is the missing piece. We always find them after they happen, and so to know this is where this object is these two objects are going to collide and create something catastrophic, we just have to watch. It's buying your tickets in advance.
Yeah. Yeah. I think it'd be terrific. Right.
And like we're familiar, my audience anyway is very familiar with the LIGO observatory, how it's sort of structured. How would a gravitational wave observatory maybe be similar or different from one that we have here on Earth?
Yeah, it would be pretty similar. Well, there are two approaches, I think. One is to build something just like LIGO, which is two beams interfering with each other and so on. You perhaps do it in a triangle, which is another way of doing it. For that, you would like to be in one of these pits of eternal darkness, the permanently shadowed regions, because it's good to be cryogenic, because then there's less atomic vibrations to worry about. And so, but it's the ideal size, at least by one group, would be about 40 kilometers on a side on an equilateral triangle. And there are only three pits of eternal darkness that are that big. And of those, two seem to be quite rich in water. So there'd be great mining targets in the somewhat distant future. And so the third one, called Faustini, is perhaps the only place on the moon where you could put that particular experiment.
But when I think about like the Earth-based versions of LIGO, these are tunnels underground that have been drilled and are kept in this very pristine environment. But with the moon, you could just stick these things outside. Like you don't have to worry about birds flying through your lasers or atmosphere or dust
that would
or
be
anything.
a great discovery, wouldn't it?
You wish you would see birds flying through your detection. So you literally could just put lasers on the moon in the right orientation, have them fire at each other, and you've built a gravitational wave observatory on the moon.
Yeah, I mean, of course, there's a fantastic number of details to make sure.
No, I just oversimplified it. Yes, I know.
But the vacuum is there. It's dark. And dark is good because you don't get dust lifted up by sunlight hitting the surface and ionizing it and charging up the particles. So you probably don't have a dust problem, which is elsewhere on the moon is a real issue. So there's good things about using these permanently shadowed regions.
That feels really compelling to me. That feels like possibly the most. I mean, getting into one of these permanently shadowed craters isn't going to be that simple, and setting up your apparatus, but it does feel like you just set up three instruments and calibrate it, and then you've got your detector, and you're taking advantage of all the natural things that the moon gives you: the airless environment, the cold temperatures, and the seismic stability. That's really interesting. I never sort of thought about the simplicity of what a gravitational wave detector might look like on the moon compared to these really elaborate structures that we have here on Earth, or even the complexity of the upcoming LISA mission.
Yeah, absolutely. I mean, the next follow-on thought is, but they're going to be people there, and they're going to be landing rockets, and they're going to be driving around in rovers and things, and won't you just get the same truck driving by problem that we had on Earth? So that's where we have to try to protect that capability on the moon, a special environment on the moon. Well, there's another way of doing a pretty amazing, to me, way of doing the gravitational waves in a similar frequency band, I believe. And that is to put very sensitive seismometers around the moon. And you don't measure the distance between the 2 points with lasers, you measure the whole moon growing and shrinking with a gravitational wave like that. And so that's apparently is a pretty straightforward thing to do. And perhaps that's a new meaning of the word straightforward that I
Yeah, yeah.
wasn't previously aware of. But
So would that be done from space? That you would have spacecraft that are like using a GPS signal to
no,
detect
no,
the position?
they would actually put them in contact with the surface. So you put them around the moon on the surface.
No, but I'm wondering how you would actually track the changes over
Yeah,
time. Yeah.
yeah.
Would they?
You measure the accelerations in the seismometer itself,
Okay.
and you know its location. And I think that you don't. It's not like interfering waveforms
Right.
together.
Right. Right.
I
You
think
you
it's
can measure the acceleration so sensitively that you can
yeah.
detect when a
That's what they tell me.
gravitational wave has gone by. Yeah.
Yes.
Yeah. That's interesting. And so once again, it's like an event horizon telescope, but it's a gravitational wave telescope and it's the whole moon.
Yeah. Isn't that amazing?
Yeah.
I'm sure you'd
Yeah.
learn a lot of good lunar stuff too, because these seismometers would be way more sensitive than anything that they put there before. So you'd learn a lot of structural. There's bound to be noise in the background there at levels we've never seen before. So,
Yeah, I
of
know
course,
the Artemis 3 astronauts right now are testing out a new set of seismometers they're going to be bringing
I
to
don't
the
think
moon as
so.
part of their mission. And they're like 10 times more sensitive
Oh,
than the ones that were part of the
yeah.
initial Apollo missions.
I think
So,
there are people trying to get some really advanced seismometers on later Artemis missions. In Europe, in particular, I believe they're quite ahead on this.
yeah, yeah. And so you're doing geology and then at the same time you're also detecting gravitational waves.
Right. The only problem is which is selling it to the right group. So you have to, if you're selling it to the lunar geologists, don't mention the gravitational waves, and vice versa.
Right.
Right? Oh, who cares about the geology of the moon? We're going to do gravitational waves. And so you've
Right.
got to tune it to
I'm
your audience, but it's the
I,
same machine.
I'm sure they are both they could come together as a team and
That would
collaborate
be
to build.
best. That would be
Yeah.
terrific. Uh, the funding sources are usually separate for geology, type planetary science, and for astrophysics. But if it's under Artemis as a general Artemis science program, then you can use both, and that's get a synergy between the two. I think that'd be terrific.
Um, Now, one of the things that I've seen quite a few papers about, and I'm not sure if you've looked into this, is the utility of the moon as a sort of historical record of the universe,
Mm-hmm.
a time machine of all of the interesting events that have happened over the last few million years. Is that being considered?
It's being talked about a lot. If you know Ian Crawford of Birkbeck College, London,
Mm.
he's written a recent review on all these things. And yes, you can get a record from the cosmic ray signal. At different depths, you've got different ages, and you can measure cosmic ray fluxes as a function of time, and you should be able to see the solar system moving in and out of molecular clouds over the course of, I think, of order a billion years or something like that, quite likely. So it's a long time, but I can't remember the right number. And it's good stuff like that. Yeah.
So I would like to put this all together then, unless there was something else. But your perspective, working with the IAU, advising them on and they're about to meet, I think,
In South Africa,
in South
yes.
Africa. Yeah, yeah. So
Sadly, I won't be going. I have booked elsewhere, but
are they going to vote? Are they going to choose? Are they going to do their version of the decadal survey and make their priorities known?
no, we're going to have sessions talking about this and trying, because this is very new to astronomers, right? So
Hmm.
things I've told you are just what we thought of so far. And my bet is, for instance, we haven't got anything talked about interferometers on the moon, where you could have a UV telescope, a whole series of them spread out, and make an array, and get micro arc second resolution or something like that, or relatively easily because they're UV. And for an interferometer, you have to know your baseline separation, and it has to be stable very accurately, less than a wavelength of the light, obviously. So that's much easier on the moon, where you just put it down and it stays put, as opposed to in free space.
It's easier to build, like say, like with those smaller wavelengths, the interferometry becomes even more difficult. Like we have infrared interferometers right now. Some attempts at visible light interferometers with, say, the
Yeah,
Very Large Telescope
yeah.
and the Keck Observatory. Although I think they've turned their interferometer
Well,
off.
that one's been turned off, but there's
Yeah,
the Chara array on Mount Wilson, which is also doing very well.
right, right. But the smaller the wavelength goes, the more difficult it is to bring that interferometer together. And so,
That's a function of the atmosphere. Take the atmosphere away, as on the moon, and the UV ultraviolet is just as good as the infrared.
and a UV interferometer has never been built before.
No,
Yeah,
because we can't. It's pointless on Earth because the UV doesn't get through the atmosphere, right?
right.
And even if it did, the atmosphere is too turbulent on those scales.
And could you scale that up? I mean, could you get into an X-ray interferometer, a gamma ray interferometer? I mean, no, it's a
Actually, people have talked about it. Certainly, a gamma ray one probably has to be in free space because the distances between the mirrors and the detector gets up to hundreds or thousands of kilometers. An X-ray interferometer design has been proposed that seems plausible, but of course, it's always the thing we do next after the one we want right now. It's never get priority, but it could be done. And again, for the same kind of reason, you want a very stable platform.
so what is like the process moving forward from this point? Like, where are you in the? I mean, the impression that I got is you took all of the ideas, summarized them together into one document, and said, "Here's the state of thinking today." What happens next, do you think?
So the thing we're trying to do is, so there's the outreach at the International Astronomical Union meeting in South Africa to try and alert a big audience of astronomers to the possibilities, and hopefully, as I say, get more ideas coming in. The other one is to get the individual teams who've been working on, say, a far side radio array to talk to each other about the kinds of environment they need, and it'll be slightly different from one team to another because I'll have different designs. And turn those, use what we call a science traceability matrix. Have you heard of this? This is a NASA term that all science mission directorate teams must follow. You say, this is a great NASA goal. Where did we come from, right? In other words, what's the evolution of galaxies and structure in the universe? And so you say, are we going to address this question by measuring the structure in the dark ages? And you gradually get more and more specific. And you're going to do that by measuring the hydrogen, redshifted hydrogen signature. And to do that, we need to have a telescope that has this sensitivity, this angular resolution, and so on, and this background noise level. And that turns into limits on where you can put it. And so it has to be on the far side, it has to be in some fairly flat region, and so on. So you go all the way from like a noble top level goal all the way down to we've got to have this level of noise. So don't put up any satellites for communications that are going to mess up that with stray radiation from their electronics boxes. Not just don't do it at all, but the total signal must not exceed this particular amount. And there's probably going to be a dozen satellites above the horizon at any point on the moon in the next 10 years. And so that some signal must be no more than that. So individual ones, probably 1/10 of that. And so we're going to do all of that. And then we'll have a very solid way to justify what we're saying. Instead of me saying, well, I looked at this with a master's student and it looks like there's only one place on the moon to put this. She did a great job, by the way, but it's not really enough to convince all of NASA that we'll have done the whole step-by-step thing. NASA has this goal. You want to fix it to get that goal? Then it translates into protecting vibrations on the moon. So, when you design your new lunar rover for people going on it, one of the criteria should be how much it impacts, what noise it produces seismically on as it trundles along. And so on, and do it systematically for all of the cases that we can think of, and then we have something we can defend.
Right, right. And the most recent decadal survey came out in 2023, like last year. Like we just went through it, and the priorities were habitable worlds observatory,
Yeah.
maybe a mission to Uranus.
In fact, there were two different decadal studies. One was
Yes, the science
astrophysics,
one and
the
the
other was with planetary. Yes.
yeah. And so are some of the solutions that a lunar platform provides, do they directly address some of the questions, some of the science priorities that were in the most recent
Yeah,
astronomy
it
decadal
was
survey?
kind of odd in that the astronomy astrophysics decadal said that the dark ages are a really important next frontier in cosmology, but nowhere in the very main recommendations was there anything to do with the dark ages. There was no talk about 21 centimeter uh, measurements, and that would have naturally led to the moon, but did not. So it's odd. I mean, there's so many people involved. It's very hard to bring all these strands together coherently. But
But but is that kind of like the equivalent of physicists saying, like a priority would be to test string theory, but how are you going to do that? So
yeah,
so let's
but
not.
I think there may have been an element of that. That
Yeah.
in the astrophysics decadal, Astro 2020, it was all a little early. The Artemis program was not as convincingly real, and I think astronomers certainly over the decades have been burnt by this. People occasionally get enthusiastic. We could put this on the moon, and then nothing happens. And or maybe NASA says we're going to the moon, and everybody gets excited, and then say no, we're going to an asteroid, right? And then we're back to the moon. So that's where we are now. But now I think it's been a change of perceived reality that the Artemis program is real. They've launched an SLS. The Starship seems to have been proven at some decent level yesterday. Um, so it all becomes much more real and much more worth thinking about. Therefore,
We've been approaching this from a sort of NASA ESA perspective.
mm-hmm.
But the Chinese just recently retrieved 2 kilograms of samples from the far side of the moon, brought them back home to Earth, or they're in the process of bringing them back home to Earth. And so they are perfecting the techniques of landing missions on the far side of the moon. They have a relay satellite that is able to relay the communications. They publish a lot of papers. I find a lot of papers that I'm looking through are teams of Chinese astronomers proposing various kinds, a lot of gravitational wave observatories, things like that. Are they considering the possibilities of telescopes on the far side of the moon? Have you looked into this?
Oh yes, and I forget the team involved. We because of this interest in the moon again. We held with Joe Silk and other folks, Ian Crawford, and we held a meeting at the Royal Society in London on astronomy from the moon. And the Chinese, one Chinese group attended, and they told us very much about their plans. And they're going to start with something like a little mother and daughter's chain of satellites orbiting the moon to make a first measurement, but then they intend to go onto the surface to establish a radio telescope there, just as we've been talking about. What scale it'll be on? Well, quite small to begin with, I'm sure. So yes, Chinese involvement is real, and they're involved in our IAU working group because that's an international astronomical union. It's completely open to all nations.
It's interesting, though. I think when you actually look at what is bound for the moon, in terms of the Artemis program, as well as supporting science platforms, there's a lot of privately built landers, rovers that are going to be carrying various science payloads. There's actually like an armada in
Mm-hmm.
development right now. We saw the lander from Intuitive Machines. There's a lot
Yeah,
going to the moon. And I think with the Artemis 3, we have humans on the moon, but there's Artemis 4, 5, they're all the way up to 8. They're thinking about 8,
yeah.
9, and so on. Do you think that requirement for more science is going to suddenly be this pull that draws in astronomical observatories to be part of this process, and is as a sort of entirely new way that this is comes into the system?
Yes, I do. I think it's very likely to happen that way at the moment. The commercial landers at the moment are just 10, 20 kilogram payloads, but of course they're the first generation. I think all the companies involved are thinking about how their next generation. I know ESA, the Europeans, are planning a 1.5 ton payload lander. Um, and of course, if when Starship, lunar Starship, can land, that's going to be tens of tons, as I understand it.
Well, let's talk about that. I mean, we both watched the
Yes.
success of Starship.
Yeah. Let's hear it
Important
for that
milestone.
flap. Hang it in there.
Yeah,
Yeah.
that fourth flap. That felt like we crossed a milestone. Like when that thing survived reentry to some degree, and it, with half a flap, that said, okay, we're into the realm of engineering problems now. But even if it's fully disposable, it is an enormous platform. Do we sort of understand the ramifications of a fully reusable two-stage rocket capable of launching 100 plus tons into space, into low Earth orbit, and who knows how many tons down to the surface of the moon? What role do you think that's going to play in our future?
Huge. Yes, I think we have not realized how this is going to change everything. People are just catching on and admitting, "Oh boy, that really is real." And I guess that, and did you hear in the commentary before launch that they were talking about evolving it to 200 tons to Leo?
Yeah,
It's
and
like,
and building one a
speed, speed.
day.
Yes, yes, it's like what? Who's going to use all that power, all that
Yeah, yeah,
capability? But
right.
they said that about Falcon 9, where you'll never, there's not enough business. And now, of course, constellations got invented
Yeah, and, and
largely by SpaceX. But
and so do you see that? I mean, do you see people going, here's my idea for a lunar telescope, and then there's a section of if Starship works, and then
yeah,
they consider the implications of a large launch
absolutely.
platform like that.
Makes an enormous difference, right? If you're landing tens of tons of equipment that can be assembled moderately easily because you have people there. Yeah, absolutely.
But
I think assembly actually becomes a little bit easier because you've got some gravity to help you, and so things don't tend to float apart, and they'll stay put. I think it could be easier to assemble things on the moon. But,
because the
in
impression that I've
engineering.
gotten is that we're not seeing a lot of that astronomers aren't incorporating that into their telescope proposals,
Yes, no, I agree, and of course,
right?
part of the reason is when you make a serious proposal, that's many human years of work. Uh, you have to propose what NASA will accept, in our case, or ESA, whoever, what the agency involved will consider as a high technical readiness level. And landing on the moon and building something there is not a high technical readiness level, whatever the future may be. It may, after Artemis 3 or 4, then maybe you'll say, okay, we can do this now, and then you can start proposing. And so the very serious efforts won't really start until after that. But I think
Right.
people need to think about it several years in advance, and so now is a good time to stay. This is getting very real. What could we do at a lower level of investigation? A few people thinking hard and being creative. Uh,
But the plan right now is to put precious human beings into this spaceship and have it land on the surface of the moon and carry them back up into orbit at a cost of $4+ billion or whatever it's going to cost to send these people to the moon on Starship, and all of the pieces of the puzzle have to come there. Like this is like if I would put it, I would put telescopes in it before I would put people in it, and yet it's people
yes,
first, and
yes.
yet it it's almost like people are really uncomfortable to dream, to hope.
Yeah, I think.
You know what I mean? They're like, but
Well, they
this
don't
is
want
like
to waste their time, right? If you dreamt of this 10 years ago or 20 years ago, you'd have just been wasting your time. I mean, you set things up for another generation of people. But now, I think it's real enough that we're getting quite a lot of interest in astronomy from the moon. And that meeting we held had probably in London had probably 50 people there. And I think getting 50 people to a meeting titled that even a few years earlier would have been impossible. People just go, nah, it's silly, waste of time.
yeah. So are there more meetings planned?
Uh, I would like to have more meetings, yes, but
Right.
it takes a bit of work to set it up. I think we need to give it a bit of time to mature, and maybe in a couple of years' time we should have a follow-up meeting. I don't know where,
Yeah. So
somewhere
Martin, what
else.
are you obsessed with right now?
What am I obsessed with? Well, Starship is what I'm obsessed with, actually. That's why I'm glued to it. Um, a year ago, I published a piece with Charles Lawrence of JPL and Sarah Seeger of MIT in Physics Today, and it was about how Starship could revolutionize how we think about missions. So I don't know if you know that the James Webb Space Telescope weighs a total of 7 tons. And so if they'd made the mirror the same way they made the Hubble mirror, that would have been 7 tons or thereabouts. So they had to invent a whole new technology to do it because the mass limit was so strict.
That was the expensive part, was shaving the mass off of every single part of that
After
telescope.
every bloody thing, yes. And that meant everything has to be just good enough not to break at 5 sigma or something, but no thicker.
Right.
Right. That whole approach is obsolete once we have a working Starship and you can send 200 tons to Leo and with refueling, and they claim it's not going to be that expensive. The same amount anywhere in the inner solar system, basically. So L2, you can have 200 tons, not 7. And so the entire way you think about building can change. But it isn't only mass, it's also the diameter of the fairing is 8 meters instead of 5 meters. And so you wouldn't have, another complication in the James Webb Space Telescope was the whole origami, as they called it, of unfolding the mirror and setting it up like that with of order 300 single point failure possibilities. That goes away, essentially. Almost all of it goes away if you can just put the 6.5 meter mirror directly into
You put the
the
tube in a tube and you launch it to
yeah,
space.
and you
Like,
and you don't need the sun shield because you can cover the whole telescope in a tube, a baffle. Yeah, it all just becomes like fantastically easier.
mm,
So we've been arguing you could probably do the set of 3 flagship missions that the Astro 2020 decadal recommended. There's the habitable worlds in the optical near infrared, possibly UV. There's the X-ray flagship based on what we call a Lynx thing, would be something like 1,000 times better than Chandra, roughly. And an infrared one, which is called Origins, and that would compare with the Herschel telescope, and it would be even faster, it'd be tens of thousands of times faster at surveying the whole sky in this pretty unexplored wavelength range. So all 3 could be done vastly cheaper if you take advantage of mass and volume that Starship allows you to do. So we've been arguing that's we should be studying this, not just hoping it works out. We should be saying, in what ways, let's take habitable worlds. And yes, they've done a lot of great work on it already, but never really with the cost and schedule being drivers. It's always the technical design, which of course is very challenging.
I think the
But
trick with this is we're in this weird limbo right now where we've seen the Space Launch System launch and we know that it works, but it's incredibly expensive.
yes,
We're watching the progress of Starship unfold as we saw success and failure and success and failure and maybe success at this point, but still we're not at that full reusability. And it's
mm-hmm.
really tricky for long-term mission planners to go, okay, fine, we're going to bet it all on Starship.
Yeah, I totally agree with that.
That is not that's not the safe bet, the one that gets people nodding
Right.
and sending
But
budget
what
your
you could
way.
do is make a side bet of a small fraction of your total effort, saying, well, what if it does work?
Right.
And what if 5 years from now, or even sooner, when we do the midterm review of the decadal study, we'll say, have to ask the question, well, what's changed?
Mm-hmm.
And but within 2 or 3 years, I would say by now, we'll have Starship working very plausibly as a kind of semi-routine thing.
You could theoretically stick that your tube, your habitable worlds observatory
Yes.
tube in the Starship that launched yesterday, and it would go to
Yes.
L2 and it would take it. I mean, maybe it would need more fuel, but it could pull this off. And
Yeah.
so I think we've already crossed that line. We're into this new regime. Yeah, it would be entirely, the super heavy would crash into the ocean. Starship would would remain in permanent orbit around the sun, or
Right.
Earth, but you would have deployed a heavy telescope. So I think that line has been crossed. And yet
Great.
I think there are architectures that are being planned that where they're saying, no, let's put this on an atlas with expendable boosters. Let's use a couple of gravitational assists, and let's spend the hundreds of millions of dollars it's going to cost to deploy this thing. And you are going down this road where you can't change
Yeah.
architecture, or it's too
Yeah.
expensive, too complicated, too humiliating to have to go back and throw everything out and go, okay,
Yeah.
fine, tube in a tube, let's do it. So I wonder if we're going to get in this sort of uncomfortable
I,
era.
I'm hoping we can. That's why we're sounding that alarm. That look, or ringing the bells. Really, of look, great opportunity, guys.
Yeah.
Let's see if we can take advantage of this and try to I guess, alert the top NASA folks who are worrying about this that maybe there's another way, and
Yeah.
but you do have to take schedule and cost as one of your drivers. Because we'd love to have 3 flagship missions, but the way it's currently laid out,
Yeah.
we won't get them till 2050 or something like that. Well, that's not a decadal plan. That's a lifetime plan, right?
And yet again, I'm so baffled that, okay, fine, yeah, like this thing is untested, this thing is provisional, who knows what's going to happen, so let's use it as our human lander. Like, for
Yes,
me, that is the
yes.
last thing I would do, right? I'd be like, okay, let's try and build. Let's let someone at night. Let's unbolt the one of the very large telescopes, and let's sneak it into a Starship and fire it off into space. Right? They're 8.2 meters. They should fit.
Well,
And
there is a plan to
8.4.
do this.
Yeah.
There are people talking about doing this through philanthropy. I don't know if you know about that.
No,
but,
no.
So I've heard.
Not the let's steal one of the very large telescopes.
No,
But let's
they
put
were
it
going to
let's
do
put
it
it
a
let's
little
put a
more
big
legitimately than that.
yeah,
Yes.
let's put a really simple big telescope in a Starship and let's just fire it off to space and see what happens. Yeah.
Yes.
Yeah.
That is being talked about for real.
Yeah. Yeah. And that feels like, okay, that crosses that line. That demonstrates the technology. That is a powerful
I wish
test.
them luck. I think that would be a terrific thing to do.
Yeah. Yeah. So if Elon Musk is listening, here you go. Stop launching these things empty. Start putting telescopes in them.
That's
That'll
right.
repair some of the faith lost with the astronomy community. Well, Martin, it's been an absolute pleasure to talk to you. Thank you so much for taking the time to chat with me today. Good luck
Okay,
with your fleet and installation of telescopes on the far side of the moon. I can't wait to find out what happened in the Dark Ages.
Me too. Okay, thank you, Fraser.
All right, take care. I hope you enjoyed this conversation with Dr. Martin Elvis. Now, I'm going to give you some additional thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, David Giltonen, Dennis Alberti, Dustin Cable, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. I will go on record as being a moon telescope skeptic. When I used to get this question from people like, why don't we put a telescope on the moon? I'm like, why put a telescope on the moon? How could this be better than a telescope in space? That with a space telescope, you look in all directions. You don't have to go into a gravity well. We understand how to do this. I'm converted. I'm convinced that, in fact, the moon is the perfect place for us to set up radio observatories, gravitational wave observatories, X-ray interferometers. These all sound like amazing ideas to me. And when I think about the kinds of science that we could do from the moon, I'm really excited, and I can't wait to see what discoveries come next. So change my vote from a no to a yes, and hopefully that will be the sort of the final vote that's required to push a lot of this science forward. All right, we'll see you next time.